Thanks, Mike. All right, good afternoon, everybody. We are Audio Pixel Alpha, as Mike said. I am Ethan Calvert. That's Jamie Sinden, Kirk Backus, Ben Bigelow, and John Winters. So the problem we started out with at the beginning of last semester that we wanted to fix, so to speak, is there's been a lack of innovation in audio technology for the last 15 years or so. In that time span, there's been a lot of advancements in video technology as far as HD TVs, LED TVs, LCD TVs, 3D technology, but there hasn't been that wave of technology that's come through with audio. Sure, there's been some advancements. There's the Sonos wireless speaker, 5.1 surround, 7.1 surround, but that's just adding a couple more speakers. There's not really a big wave of innovation coming with that. So what we decided to do was create an interactive experience for our user. So pretty much we wanted to immerse the user in almost an exhibit-like experience where they can control the position of audio on a fairly big grid of speakers. We're talking 24 speakers, so it's 6 by 4 on a grid of speakers.
Going into this, I turned on. Hello? Okay. Going into this, we had to make some decisions about some design requirements that we were going to set for ourselves. The first big one was that we needed our system to be reliable, so obviously we don't want the system to crash. Secondly, we need to be accurate, so we need the placement of the sound based on the hand gestures to be in the right location on our sound grid. Third was portable. It's a fairly large grid of speakers, so we designed the grid to be broken down into parts so it could be moved by a small group of people. And lastly, we need to be efficient, so efficient modular coding so that it is able to be expanded upon. So going in this, we knew it was a new technology, and there's a lot of possibilities for new advancements. So we really just wanted to lay the foundations and set down some basic functionality that other people can work off of.
Okay, so we started with 80/20, and we designed a grid, which is in 6 different sections. There's 3 wide, 2 tall. Each one's 4 by 4. That makes it about 8 feet tall and about 12 feet wide. There's 24 speakers or pixels that are all linked together through Cat6 cable and into an Ethernet switch. All of them are plugged into the 100 megabit switch port, except for the server, which goes into a gigabit switch port. And then the server, which is a personal machine, as well as works with the Kinect to actually get all the hand gesture recognition. So the Pixel itself is, as you can see here, on the front of it we have a 2-inch flat speaker from NXT, and then on the back we have a Raspberry Pi, which is a small computer. And then on the inside of it you can see we have a Chemo mono amplifier, and then we have a voltage regulator, we have a power switch, volume, and all the essentials you need to pretty much control it, and as well as a fuse just for protection.
For our client hardware, we used a Raspberry Pi, which is a very basic computer about the size of a credit card. We used it because we needed some minimal computing capability on our client side. And Raspberry Pi has 2 models, Model A and Model B. We used Model B, which has an Ethernet port. We wanted to have our clients on a local Ethernet network so that we could transfer our audio as quickly as possible and prevent any loss of sound or distortion.
So for gesture recognition, I'm good, okay. For gesture recognition, we used the Windows Kinect. There was multiple other options out there that we could use, but we felt the Kinect was the most mature out of all the technologies that are out there. It's got full skeletal detection. You can customize the gestures that are used that are when you're being detected. Like I said, there's other options out there that weren't as mature, and there wasn't as good enough documentation for us to go off of. And we felt that with the other parts of the project being pretty complex, we need to make it easier on ourselves and just use something that's pretty mature and has been tested. Whoops. So for the network, we're using a UDP connection, so to speak, a unicast connection. When we originally started, we wanted to use TCP, but we were having issues with the audio not being sent fast enough because of gaps in playback. So one speaker would fall behind the other one, and it wasn't synchronized properly. And that was because with TCP, it makes sure that every packet is sent, and if it's not sent, it'll try to resend it, and that made the audio become unsynchronized. So we decided to go to UDP, since we didn't really need to have a connection all the time. We just needed to generate the audio on the server and send that audio over the network as quickly as possible. So we want to be playing in real time and as soon as possible. We're doing that on the server through the use of an asynchronous UDP socket, which just is called every time a audio needs to be sent over the network. It goes through this socket to be sent over the network. So for our server software, not sure what's going up with the resolution, but we used Visual Studio as our IDE and the C# language. And for our application, you can't really see, we use a WPF application, which is Windows Presentation Foundation. We made this so we could interface with the grid. It's got a virtual grid, so to speak, on the interface, and it also gives the user feedback of where they are compared to where the Kinect is detecting you at. So on the client side of things, Jamie's going to talk about that.
For the client software, we were originally wanting to write our own audio streamer to be able to play back the sound that we got from the server. But we had some difficulties with C libraries trying to find something that would work the way we wanted it to. We discovered GStreamer, which is a streaming library that's built into C, where we could give it a server to connect to, and it would take in the audio stream and play it back.
All right, and considering how we were actually sending these sounds, these parts of audio to the clients, we decided to use wave audio. And if you're not familiar, wave audio is just literally the waveform that is stored in amplitude in digital memory, and that is eventually transformed into an analog audio signal that we can hear. And the reason we chose this is because it's very easy to use and manipulate. One of the cool properties is, since it's just the amplitude being sent to the clients, we can actually split up the amplitude on different speakers. We employed something known as bilinear interpolation, which allowed us to move the stream across the grid smoothly. So as you see up here, we have what's our stream here is in the middle, and most of the sound will go to this little yellow one up here based on this ratio. And what this allowed us to do is move the streams across. So instead of going from jumping from one speaker to another, and the grid's pretty wide and tall, we'd have this very nice smoothing effect as we go across. Another thing I'd also like to talk about is the UDP aspects of the project too, because when we're using UDP at 44, let me back up a bit. Sampling the wave, we use 44,000 hertz. The reason this is important is because of the sampling theorem states that in order to have perfect reconstruction of a signal, you need at least twice the frequency in your sampling frequency of the frequencies that you need to represent. For example, human hearing is from 20 hertz to 20,000, so we needed a sampling frequency at least 40,000 hertz. And so we chose the de facto CD sampling, which was 44,100. There's some great advantages to that is that the packets that we send in UDP only contain about 2,048 bytes, and that's about 1,024 samples. And why that's really nice is if the packet doesn't get there, well, we only lose 22 milliseconds of audio, which is very difficult to discern sometimes. So if it gets there, it's great. If it doesn't, that's not that big of a deal. So
with that, here is what the grid looks like. As John said earlier, this is made with 80/20. Each of the speakers is what we call a pixel. They're placed 2 feet away from each other, horizontally and vertically. Each one of them is connected to this power supply here. It's just a regular 750 watt PC power supply. And each one of those is connected to the network switch, which is missing. But it's over there. how to use this thing right there. Each one of the pixels is connected there. We had issues with heat problems, so we had to put in these heat sinks on the side here to prevent overheating. It would give the heat more of a surface area to escape the inside. So here is pretty much how it looks with the setup. This is our interface. You can see right here, this is the synthesizer options. These will send the sound through a synthesizer to create different types of sounds that you can hear. Here's the view of the Kinect to get the user where they are relative to the Kinect's view. Here's their hand that moves with the user's hand, and these are each of the individual pixels. This is just the virtual grid that is displayed to help the user determine where their hand is placed at the given time. With that, we have a quick little demo. I don't know, we might have to make sure the sound's not too loud. So what's going on right now is the Kinect is detecting the gesture, which is just a simple hand motion. The Kinect is sending a stream to the server. The server is parsing that information. And as she's moving, the sound is being interpolated through to four different speakers at a time as she's moving across. So right now, it would be to the bottom right 4, the middle 4. Obviously, since the grid's not here right now, it doesn't give the full effect.
One of the reasons we chose also synthesis of audio is so that we could prove that this was actually happening at real time, and this was not just something that we kind of predetermined. So as you can see up here, we associated each one of the speakers with a different note, and it sounds kind of funky. But you can see that they're producing different noises, and unfortunately, we couldn't bring in the speakers, so I don't really get that full effect as Ethan mentioned. But it's, yeah, this is pretty much what we did.
So, as we mentioned earlier, what we wanted to do was make something that was expandable upon, and give future users, hopefully, that come and work on this project, the ability to build upon what we've done and add even cooler features to what we've already set out there for them. So with that, that is our presentation. And any questions?
I have a quick one. So very cool. I'd love to have one in my home. What are some practical, you think, applications for this technology down the road?
Really, it could be anything. For right now, what we're thinking is more of an exhibit-like experience you'd see in a museum, like a kids museum or a children's museum. It'd be fun for them to go around and mess with different sounds and be able to place audio on a different side of the grid. Really, you could do anything. You could put one of these speakers in your home somewhere and connect it wirelessly and be able to tell which speaker in your house you want to be playing music at a given time.
One of the things, you may have noticed some of this went right over the top of my head, and that often happens when we're working with our technology colleagues, but we do learn at RJI. For example, we've learned just from this team and from another team we're working on some of the possibilities of Kinect. We're working with some engineering folks and folks from the medical school on a project to use this same sort of sensing technology to help athletes to treat sports injuries. We knew nothing, at least I knew nothing until this semester about Raspberry Pi, but not only is this team using it as part of their technology, but Team Place was also using it as a way to gather their video and share that in real time with their applications. So we learn an awful lot over time from our colleagues in computer science and IT, and we really appreciate your presentation this morning. Thank you.
Thank you.
Oh, yeah.